Here's a box of atoms jiggling with heat. Lower the temperature and what do you expect? They slow down, they calm. Common sense says a cold gas just sits there, sluggish, spread thin, so watch this. We keep cooling and at one precise temperature something absurd happens. A billion separate atoms stop being a billion separate things and become, in a real physical sense, a single object. Not frozen, not merely slow. This is bose-einstein condensation, and the puzzle is right there in the contradiction. Cooling should spread things out and quiet them down. How could it instead make a crowd collapse into one? Hold that question. To unravel it, we have to drop a comforting lie, that an atom is a tiny ball sitting at a point. Basic quantum mechanics already told us otherwise. An atom is a wave, a smear of probability with an actual width. Picture that width as a soft cloud. And here's the part that feels backwards. The colder and slower the atom, the longer its wavelength, the wider that cloud spreads. Cooling doesn't shrink an atom's quantum size. It grows it. Keep that close. It's the hinge the whole story turns on. Let's put a number on that width. We start from something you already trust, Broglie's relation. An object's wavelength equals Planck's constant divided by its momentum. Now in a warm gas the momentum isn't a single value, it's set by temperature. Swap in the typical thermal momentum, and after the dust settles you arrive at the thermal Broglie wavelength lambda t. Let's read it piece by piece. Up here, h bar, Planck's constant, the basic quantum of action. Here m, the atom's mass, heavier atoms make smaller waves. Here kb, Boltzmann's constant, the bridge that turns a temperature into an energy. And down here in red T, the absolute temperature. Notice where T sits underneath inside a square root, so lambda T is proportional to 1 over root T. Now watch what that means on the graph. As T falls toward absolute zero, lambda T does not shrink, it climbs and keeps climbing without bound. Every atom's matter wave swells as the gas gets colder. That single fact is the engine of everything that follows. Now the key question turns geometric. In the gas, atoms sit some average distance apart, call that spacing d. Describe how tightly they are packed by the number density n, how many atoms per unit volume, and that spacing is simply n to the minus 1/3. Two regimes. When the matter waves are tiny compared with d, each atom is its own little wave in its own little box. They ignore one another, it's an ordinary gas. But as we cool, lambda t grows toward d. The clouds reach out and touch, they overlap. And the instant one atom's wave blurs into its neighbors, you can no longer say which atom is which, and the whole quantum statistical character of the gas switches on. So set lambda t equal to the spacing, cube both sides, and the geometry collapses to one clean dial. N times lambda t cubed. When that crosses about 1, the waves overlap and condensation begins. But about 1 should make you suspicious. It's a hand wave, an order of magnitude guess that hides an exact answer. Let's be honest about the real number. If you do the full bookkeeping for an ideal gas of bosons in a box, actually adding up how many atoms the moving states can hold, the threshold is not 1. It's a specific constant, the Riemann zeta function of 3/2, which works out to 2.612. So let's go back and fix our earlier claim. The onset is not n lambda t cubed is about 1. Strike that. It is n lambda t cubed equals 2.612, exactly. And that clean number is precisely why we chose this convention for lambda t in the first place. So the constant from the statistics lands without clutter. And now the real heart of it, why a single state, and why a huge fraction of all the atoms. Think of the energy levels as a tall staircase of rooms above one ground floor. Bose statistics has a strange permission built in. Any number of atoms may pile into the very same state. They love company. Here's the twist. At given temperature, all the moving rooms on the staircase, taken together, can hold only so many atoms, and that ceiling is exactly the 2.612 we just found in disguise. As we cool, lambda t grows and that ceiling drops. So ask yourself, below the critical temperature when the staircase can no longer seat everyone, where do the leftover atoms go? Think about it. They have exactly one place left, the ground floor, the single lowest state. And because bosons can share without limit, that one floor swallows them by the millions. That is the condensate, not atoms huddling together in space, but a macroscopic crowd forced into one quantum state, every one of them described by the same single wave. Is any of this real? In 1995, in Colorado, Eric Cornell and Carl Wieman did it with rubidium-87. They cooled about 2,000 atoms to 170 nanokelvin. That's 17 10 millionths of a degree above absolute zero. To feel how cold that is, the coldest natural place we know, the empty space between galaxies, sits at about 2.7 Kelvin. Their gas was roughly 16 million times colder than that. And at that temperature, each atom's matter wave had swollen to about half a micron, the wavelength of green light, which is just about the spacing between the atoms. The waves touched, exactly as predicted, and a sharp spike appeared, a tower of atoms all sharing one state. Bose and Einstein had written this down on paper 70 years earlier. So return to our opening box and our contradiction. Cooling really did spread each atom out, that part was true all along. But spreading them out is precisely what made their waves overlap. And once the waves overlap, statistics does the rest. The crowd has nowhere to fall but the single lowest state. The paradox dissolves. Cooling never quieted the gas into stillness. It grew every atom until they all became one wave. There is your answer. Here it is for a curious 12-year-old. Every atom is a tiny ripple. Cool the water and each ripple spreads wider. Cool enough, and the ripples all overlap, blur together, and stop being separate. What's left is one big ripple, every atom singing the same note. 5 steps to carry home, and they spell merge, which is exactly what the waves do. M, every atom is a matter wave, a cloud of size lambda t. E, cool it and that cloud expands, growing as 1 over root t. R, keep cooling until the clouds reach each other and overlap. G, the genuine threshold isn't 1. It's 2.612, and E, with the moving states full, everyone left over pours into the single ground state. Matter, expand, reach. Genuine everyone, they merge. One last thing to chew on. If a condensate really is a single wave, then take 2 separate condensates, release them, and let them fall through each other. 2 waves meeting do what waves always do. So, what would you see in the region where they cross? Don't rush it. Sit with that.